in just a moment. Welcome to the 2025 ACI Virtual Undergrad Research Session. On behalf of President Maria Younger, we would like to welcome you all. The ACI Foundation provides undergraduate and graduate students with opportunities to receive fellowships in the amount of $10,000 USD for students enrolled in a university in the USA or Canada. All students, including international students, can apply to receive a $5,000 USD scholarship. The application period will open on July 1st and close on November 1st. Learn more at www.acifoundation.org/scholarships. The James Instrument Student Award for Research on NDT of Concrete is now open. The competition is sponsored by the ACI Committee 228 and will award a cash prize of $1,500 to a student pursuing research related to non-destructive testing of concrete materials and structures. December 1st is the deadline to apply. The Egg Protection Device competition will take place this fall in Baltimore, Maryland, USA. The objective of this competition was to design and build the highest impact load resistant plane or reinforced concrete egg protection device, EPD. Learn and report on concrete sustainable benefits related to durability, impact resistance, and other real life aspects which an EPD simulates. Registration is now open and will close October 3rd. Visit the ACI website at www.concrete.org/students to learn more. And now I would like to turn this portion of the program over to the S805 Student Leadership Council. S805 is ACI's only student-led committee. The mission of the Student Leadership Council is to provide students with the tools to successfully run an ACI student chapter, develop presentations and public speaking skills, and prepare students for leadership roles within ACI communities. Students interested in joining S805 should submit their application online at www.concrete.org/get-involved/committees. Without further ado, I'll turn it over to my S805 leaders. Thank you all.
Hello, everyone. I'm your committee chair, Vanya Moreno-Collin. I'm a master's student at the University of Illinois, Urbana-Champaign.
Hi, everyone. I'm Adam Johnson. I am a PhD student in civil engineering at Penn State.
Hi, everyone. I'm Mohammed Al-Shara. I am another co-chair of the committee, and I'm doing master's at Clarkson University.
Hi, everyone. I am Akriti. I'm doing my PhD in North Carolina State University. I'm the secretary of the council.
Perfect. Thank you all. It's wonderful to meet you all. For those who haven't met our Student Leadership Council, we are pretty much going to get right into it. Our chair is going to pretty much get our presentations kicked off for us.
If you're from Chittagong University of Engineering and Technology and are presenting on carbon negative mortar, can you please raise your hand so I can unmute you?
Okay, if our representatives of Chittagong aren't quite here so far, we are going to go ahead and proceed with their presentation. If anyone has any questions, we can be sure to get those over to the university students.
In that case, we can move on to National University of Science and Technology. Can you please raise your hand if you're presenting on formulation of printable mix design for prefabricated beams? Okay, we have one. Muggies? Are you able to unmute yourself?
Yes. Hello, I'm Giskani and yes.
Perfect. Thank you for joining us today.
And can everyone see my screen all right? Perfect.
Hello everyone, the topic of our research project is formulation of printable mix design for prefabricated beams. Here's our team, here's the table of contents, and for introduction, let's begin by having a look at crisis that affects every corner of Pakistan, which is housing. Our population is increasing rapidly, but we're only able to meet 35% of housing demand every year. Housing prices are skyrocketing, but GDP per capita has barely increased. So how can we solve Pakistan's housing and infrastructure crisis? Not through patchwork fixes, but with technology that fits our context. Traditional construction, which is currently implemented in Pakistan, suffers from extended project timelines, which decreases the productivity. Labor accounts for up to 30% of total cost, and high energy consumption makes this process environmentally unsustainable. Globally, we've seen alternatives like modular construction, automation, and robotics, but one promising solution which combines the benefit of all three is 3D concrete printing. It is a layered form of free technology which uses where concrete is deposited through robotic extrusion. It starts with a digital design formulated by material formulation and ends in robotic extrusion. The final step is curing and finishing. It has a lot of benefits and it replaces the most time-consuming and costly steps in traditional construction. In normal mix, the only fresh property we care about is workability, but in 3D concrete mix, you need print mix properties and process parameters, and they both have to be in harmony in order to achieve a successful print. In literature review, we found that 3D print mix uses complex additives, which increases the cost and makes it complex to reproduce locally and scale. The printed structures have higher chances of shrinkage, so we can use fibers. Steel fibers, however, disrupt the print quality, but polypropylene fiber offer a fire-resistant alternative. 3D PC still has higher quantity of cement, so we found a sustainable partial replacement, which is metakaolin, and it also improves the compressive strength. In 3D PC, 80% of research is done on mixed design, but only 1% research is done on building level integration. And within that 1%, walls and columns are commonly printed structures. So we wanted to print and optimize beams such that they balance the material use and mechanical properties. Based on the literature review, we formulated two problem statements. And based on these two problem statements, we defined our objectives and divided our project into three corresponding phases. So in phase one of our research, our objective was to develop a simple, sustainable, and of course, a printable concrete mix design. This is an overview for phase one. After selecting process parameters and adequate mixing, each mix was assessed based on a number of fresh and hard properties. All our materials were locally sourced, and here's the rationale for the selection of each material. Now, this slide gives an overview of the effects of each printing parameters on printing, and that each plays an important role. For print, chose a circular nozzle as it facilitated the printing of complex geometries. Nozzle size was kept at 25 millimeters as it struck a balance between good printing resolution and good printability. Stand-off distance was kept at 15 millimeters, which gave good interlayer stability. Next, print speed and extrusion rate were experimentally kept in sync to avoid breakage or flat elements. And lastly, interlayer interval time was naturally about half a minute due to our short print paths. So this is the mixer standard which we developed for the smooth flowable mix. And in this phase, we tried a total of 27 mixes, out of which we chose representative 8, which I'll shortly discuss. So coming over to evaluation of our mixes, first we looked at the fresh properties. For the flowability, initial setting time and slump flow tests were performed, while extrudability and buildability were inspected visually. Here, the first three mixes fell in the zero buildability region and were too flowable, while the last three were not extrudable due to being too stiff. Mix 4 and 5 fell in the optimum slump range, and mix 4 was chosen as a base mix due to superior print quality. The initial setting time test showed the same trend, and using that correlation, we drew an optimum range for adequate flowability. These are some examples of poor extrusion. As can be seen, the expected and actual widths do not match, while these two on the right are examples of good extrudability as the expected and actual widths do match. Moving over to another fresh property, buildability. The upper layers of these specimens have collapsed due to elastic buckling, which occurs when interlayer instability is present, and that happens when now the stand-off distance is too great. Again, this print is failed in terms of buildability, this time due to another phenomenon known as collapse.
And the bottom layers have essentially flattened under load due to insufficient yield stress of the mix. Now these are some successful prints. As can be seen, layers are fairly uniform and stable. These are some more members which have been extruded successfully, and again some more successful prints.
Once we established our base mix, we sought to improve certain properties of our base mix with the addition of polypropylene fiber and metakaolin. This is an overview of our methodology for phase 2. To improve crack resistance of our mix, we added the polypropylene fibers. This is the trial range we used. 2 and 3 were rejected because their print quality was too poor. Furthermore, to improve the thixotrophy of our mix, we added metakaolin to it. This is the trial range for that. Above 5% dosage, the open time of our mix became far too less optimal for printing, hence we went with 5%. Again, for these mixes, we performed the same tests as those used for our base mix. Both M2 and M3 fell in the optimum flowability range, which we established while developing our base mix. M2 and M3 also passed extrudability criteria. All mixes had deformation below the limit stated in literature, so buildability wasn't an issue either. All 3 mixes also had adequate strength. This is an overview of our compressive strengths. Printed specimens showed higher strength due to the compaction caused by the nozzle of the printer. These are the plots between compressive strength and ultrasonic pulse velocity values of the specimens. This correlation can be used to predict strength of printed specimens as they exhibit higher strength variability. Lastly, we measured bond strength using this setup, and our strengths fell within the range reported in literature.
So for the third and final phase, we wanted to test 3D PC beams both experimentally and numerically. Here is the overview of our third phase. As mentioned earlier, 3D CP allows us full architectural freedom and to print optimized geometries whilst reducing the material usage and the self-weight. For this reason, we chose 2 geometries, the first one being the truss infill beam, which reduces material usage at low stress points, and the second being the arch infill beam, which efficiently distributes compressive loads. Both the beams were printed using the M1 and the M2 mix. All the 4 beams were tested under the center point bending test, and the crack initiation was observed for all the 4 beams. Now, a common observance was that the cracks developed near the joints where the stress concentrations were high, mostly in the bottom fibers, and the fiber reinforced beams exhibited a ductile failure. Based on the experimental results, we chose the arch fiber beam as the beam with the highest flexural performance, having a 10.81% increase in the load carrying capacity and a 124.2% decrease in the material usage as compared to the cast beam with fiber reinforcement. This exceptional increase in the load in the flexural strength of the arch infill beam can be attributed to the high degree of fiber alignment observed in 3D printed beams as opposed to a cast beam in which the fibers are randomly dispersed. For the numerical analysis, we modeled the arch infill beam in Fusion 360 and imported it in Abacus. We used the to simulate our tests. We used a tight interaction between the layers, used static general for monotonic loading. We used roller supports on both sides to mimic the real-life experimental conditions, and used an 8-node linear brick element for the meshing. Now, if you look at the experimental and the numerical results, we can see a high degree of similarity between the both, where the cracks occurring near the joints. Comparing the experimental and the FE results, we saw a 7.49% error in results, which can be attributed to the printing inconsistencies. However, this error was within the acceptable range as given in the literature. We have been awarded research grants by the 4G Cement Company Limited, Vertex Chemicals, and Ignite National Technology Fund, and our project has been endorsed by UNESCO. In conclusion, we achieved what we sought out to achieve at the start by successfully formulating a locally sourced printable mix design. We enhanced this mix design using metakaolin and PP fibers, and finally we selected a lightweight 3D printed beam geometry through experimental and FE analysis in the arch infill beam. For our future goals, we want to optimize this 3D printed arch infill beam via a parametric study. We aim to perform some durability tests for our 3D PC mix, and finally, we want to explore other suitable low-carbon materials in Pakistan. Ladies and gentlemen, thank you so much for your time. We can now proceed towards the Q&A session.
Any questions?
Start us off. How soon do you think something like this could be implemented into industry standards and, be part of our code?
Thank you so much for the question. I believe we are still at the infancy of this technology. As far as 3D printed beams are concerned, there's a call for more research on 3D printed structure elements, especially beams and slabs. So as far as the industry adoption is concerned, I think that we need more research, we need more data, and we need and we especially need more research on its constructability, as well as we need more parametric research to optimize the beam shape. So I think it could take about 4 to 5 years before we establish a proper theoretical framework on its design and its constructability.
Thank you. That's exciting stuff.
Perfect. Well, if we don't have any more questions, then we will jump right next to our next presentation. Thank you so much for your presentation, everybody. Thank you so much.
Next up, we have the University of San Francisco de Quito. Can the representatives raise their hands? Perfect. All right, with that, we'll get started.
Hello, everyone, and thank you for joining us. My name is Daniel Abril Camino, and I am speaking on behalf of my research partners, Juan Martín Tamayo and Tommy Silva, students at the Universidad San Francisco de Quito in Ecuador. We are proud to present our work titled Mechanical Performance of Concrete with Recycled Aggregates and Natural and Synthetic Fiber Reinforcement. This project was developed under the guidance of our advisor, Dr. Francisco Jate. We are excited to share our findings with the ACI undergraduate research community, and we hope this contribution supports further innovation in sustainable concrete technologies. The construction sector faces a critical challenge. Nearly 60% of the urban area projected for 2030 is still unbuilt. This surge in infrastructure demands translates into massive resource use, especially cement, increased debris, and a heavy environmental footprint. Globally, construction generates about 25% of greenhouse gases, consumes 40% of energy, 16% of water, and produces up to 40% of solid waste. A sustainable response is recycling construction and demolition waste, focusing on concrete, the most used anthropogenically material. Yet, recycled aggregates often have lower quality and higher impurities, raising water absorption, reducing workability, and weakening strength. Fibers, particularly polypropylene, can improve tensile resistance and limit cracking, but they are not eco-friendly. Here, natural fibers like coconut and abaca, abundant in Ecuador, emerge as a greener alternative. This study, in collaboration with Holcim SA, evaluates concrete made with recycled aggregates and natural fibers, comparing it against traditional mixes with natural aggregates and synthetic fibers, aiming to propose sustainable large-scale solutions. We processed 180 tons of construction and demolition waste, removing unsuitable materials like steel, plastics, and general debris. The aggregates were classified under ASTM standards into three gradations, number 57 stone, number 7 stone, and sand, with only 1% discarded as non-usable material. Recycled aggregates were obtained through debris collection, manual sorting, and metal removing using an electromagnet. For reinforcement, we used three fibers, commercially available polypropylene fibers, as the synthetic control, with a length of 2 inches and a diameter of 0.03 inches. The natural fibers, abaca and coconut, were sourced from Ecuador, Santo Domingo and Manabí provinces respectively. Both natural fibers were 4 inches long with a diameter of 0.008 inches. The modulus of elasticity of the natural fibers was tested at the Materials Laboratory of Universidad San Francisco de Quito, with the results presented. The aggregates were first tested for radiation, density and absorption, abrasion, uniformity, and alkali-silica reactivity, following ASTM standards. Two concrete formulations were designed. The first used number 7 stone and sand due to formwork geometry, with a water cement ratio of 0.45 and 60% aggregate by weight, 60% coarse number 7 stone and 40% sand. The cement was type GU, a general use pozzolanic cement in Ecuador. 6 mix were produced, 3 with natural aggregates combined with synthetic and natural fibers, and 3 with recycled aggregates using the same fibers presented. From each batch, we cast 4 prisms, 20 inches by 6 inches by 6 inches, and 6 cylinders 4-inch diameter by 8-inch height. 3 cylinders were tested in compression, and 1 was sliced into disc of 1 inch thick for dynamic modulus testing. For tensile test, dove-bone specimens were cast, 4-inch long with a 2.5 square inches cross section and a triangular ribson 2-inch high and 5.5-inch wide. Cement paste was used with a 0.4 water cement ratio and favored dosage of 2% and 5% by volume. We prepared 3 specimens per dosage, totaling 18 fiber reinforced samples plus 1 reference sample without fibers. We evaluated the mixes through 4 tests: compressive strain, flexural strain, dynamic modulus of elasticity, and direct tensile strength. Compression tests were performed on 4 per 8-inch cylinders after 28 days of curing. Flexural strain of the fiber reinforced prisms was measured following ASTM C1609, also at 28 days. A key parameter of this study was the dynamic modulus of elasticity, assessed on 4-inch disc, 1-inch thick, made with different aggregate and fiber combination. The test followed Hutchinson's model of flexural vibration of circular plates with free boundaries, where the modulus is derived from the natural vibration frequency. The procedure involving dropping a 150 grams steel ball on the center of each disc. A high-frequency accelerometer was glued to the opposite side, and its signal amplified and sent to an oscilloscope. Using MATLAB and a fast Fourier transform, we extracted the dominant frequency to calculate the modulus based on Lemming studies. Direct tensile strain was measured on dove-bone specimens cured for 14 days. A speckled pattern was applied for digital image correlation DIC to capture strain. The tests were performed on a universal machine with custom grips at a loading rate of 0.08 inches per minute. The recycled aggregates showed a marked increase in water absorption compared to natural ones. For coarse aggregates, absorption was about 2.5 times higher, while recycled sand reached an absorption rate over 10 times that of control sand. These values reflect the presence of residual mortar and the higher porosity typical of recycled materials. In contrast, density decreased. Coarse recycled aggregates dropped by about 7.5% and recycled sand by roughly 22% compared to their natural counterparts. These results are illustrated in bar graphs, where the x-axis represents each type of aggregate and the y-axis shows the corresponding values for density and absorption. To evaluate alkali silica reactivity, 6 more terms, 1 by 1 by 11 inches, were prepared, 3 with recycled sand and 3 with natural sand, and submerged in sodium hydroxide and 176 Fahrenheit degrees for 14 days. Expansion was measured daily. Both sands showed similar trends, an initial expansion that quickly stabilized and remained well below the 0.1% critical limit defined by ASTM C1260. This suggests that neither sand presents a significant risk of internal expansion. These results are shown in a line graph with time on the x-axis and expansion on the y-axis. We performed 3-point bending tests to measure peak flexural strain, post-cracking behavior, stiffness, and energy absorption of the fiber reinforced mixes. In terms of ductility after cracking, all beams meet the minimum deformation required, the standard about 0.14 inches, except the one with coconut fiber and natural aggregates, which reach only 0.07 inches, roughly half of the required value. This confirms that the proper addition of fiber significantly enhances post-cracking ductility. For peak load mixes with recycled aggregates and natural fibers showed the reductions about 2/5, 1/4, and 1/3 compared to the control mix with polypropylene fibers and normal aggregates. Analyzing post-peak behavior, all beams except those with abaca fibers maintain relatively stable strength after the maximum load. Beams with polypropylene fibers resisted on average 15 kilonewton after the peak, those with abaca fibers about half of that, and those with coconut fibers roughly 1/3. Toughness measured as the area under the load displacement curve varied notable with a fiber type. Polypropylene fibers achieved the highest energy absorption around 54 joules. Abaca fibers reached about half that value, while coconut fibers showed roughly 1/4. These differences reflect the higher energy absorption capacity of synthetic fibers compared to natural ones. The direct tensile test confirmed the same pattern seen in flexural behavior. At a 4% dosage, mixes with synthetic fibers show the highest deformation capacity and energy absorption compared to the natural fibers. However, maximum tensile strength revealed a different trend. At the lower dosage of 2% natural fibers, especially coconut and avocado, outperformed polypropylene. At 4%, coconut and polypropylene reached similar peak strengths, while avocado achieved the highest tensile strength of all mixes. This gain in strength with avocado, however, came with reduced deformation capacity compared to synthetic fibers. In peak flexural load, coconut fibers were the strongest with natural aggregates, carrying a little over 45 kilonewtons, while polypropylene followed just about 40 and avocado slightly below that. With recycled aggregates, coconut again led at around 30 kilonewtons, very close to avocado, while polypropylene dropped noticeably to about 25 kilonewtons. For thoroughness, recycled aggregates had a clear benefit. With synthetic fibers, energy absorption reached around 55 joules, well above the values of the same mix with normal aggregates. Overall, the fiber type defined the response. Synthetic fibers delivered the greatest toughness, while coconut fibers allowed lower energy absorption. Decompression using recycled aggregates lowered the strength by roughly 1/3 compared to normal aggregates. Even so, coconut and avocado fibers added a slightly recovery, likely due to internal cooling from water retention. Fiber type did not change compressive strength directly, but it did influence curing behavior. In direct tension, every fiber reinforced mix surpassed the baseline cement paste. Avocado fibers stood out, reaching up to 2.12 megapascal, followed by coconut and then polypropylene, which improved notably at higher dosage. Here again, synthetic fibers allowed larger deformation, indicating greater energy absorption capacity. The dynamic modulus of elasticity was measured at 30 and 240 days. In all cases, the resonance frequency increased over time, indicating a higher modulus and overall stiffness. With natural aggregates, the largest gain came from mixes with polypropylene fibers, up by about 7%, followed by coconut at nearly 7% and avocado with a minimal risk of less than 1%. For recycled aggregates, the same trend appeared, but with smaller increases. Polypropylene up nearly 5%, coconut about 3.5%, and avocado around 3%. Over time, resonance peaks also became more symmetrical, suggesting improved internal structural stability. However, mixes with coconut fibers showed the greater variability due to workability issues. Fibers tended to clump, creating heterogeneity. This was visible in the Fourier transform results, where the peaks were more irregular from as early as 30 days. Finally, the key findings. We developed sustainable concrete using recycled aggregates and natural fibers like avocado and coconut. Recycled aggregates boosted toughness by about 1/3, but lowered the dynamic modulus by nearly 1/5. On the strength side, they reduced compressive strength by roughly 1/4 and flexural strength by about the third. Compared to polypropylene, natural fibers absorbed less energy, about half with avocado and less 1/3 with coconut. But at a 4% dosage, avocado achieved the highest tensile strength among all natural fibers. Polypropylene at 4% offered the greatest deformation capacity, while all fiber reinforced mixes surpassed the tensile strength of plain cement paste. Part of this work was published in a scientific article developed by the Universidad San Francisco de Quito. I am attaching a QR code that links directly to the publication for further reference. Thank you very much for your attention.
Thank you for that presentation. Daniel and Juan, do you want to unmute yourselves, answer any questions?
Yeah, if there's any question to answer it.
Yeah, I have a question for you guys.
Yep.
How did the different fibers and aggregates affect your workability?
Okay, so the natural fibers absorb a lot of water. So when we use them, the water that we put in the mix was absorbed a lot because of these fibers, and it made it really difficult to work with the mix. To put the concrete in the cast, it was really hard for us because we have to vibrate a lot, and we had to like mix it a lot so the concrete went inside well in the cast. Also, as you saw in the presentation, the recycled aggregates had a lot more absorption than the natural aggregates. So these also absorbed a lot of water. And when putting both the natural fibers and the recycled aggregate, like most of the water, instead of mixing with the cement, it went to the recycled aggregates and natural fibers. This generate like a really low workability, and we like battle a lot to put all in the cast. That through the vibration system, we had a vibration table, and by with help of some glue hammers, we managed to put it all in the cast, but it was really, really difficult. I don't know if that answered your question or you have anything else to ask.
That answers it. Thank you, Juan. Does anyone else have any more questions? Okay, with that, we can move on. Next up, we have the University of San Francisco. Oh, we already did them, sorry. Wayne State University. Can representatives please raise their hands? Okay, let's get started with this one.
Hello, my name is William Cothran. I am an undergraduate student at Wayne State University under Dr. Mersini Maglogiani, and I am presenting on enhancing the performance of PLC concrete using carbonated aggregates and carbon-based nanomaterials. Every construction project from new apartments downtown to revitalize neighborhoods relies heavily on concrete. Concrete needs aggregates from natural sources, which means mining and extracting from our environment. At the same time, old buildings and structures around Detroit are frequently torn down, creating large amounts of debris. Usually this debris ends up in local landfills, taking up valuable space and harming the environment. Our research motivation is to use this demolition waste by substituting part of the natural aggregates with recycled concrete aggregates. Using recycled concrete aggregates, or RCA, in construction offers many advantages. By recycling the construction waste into usable recycled concrete aggregates, we can reduce landfill waste and limit the need to extract natural resources, protecting the environment around us. RCAs are also more cost-effective than natural aggregates, making an overall cheaper mix design. Some of the disadvantages of RCAs include the porous structure and the weaker interfacial transition zones, as illustrated in the schematic on the right, comparing natural aggregates to RCAs. Unlike natural aggregates, RCAs contain a double ITZ layer, the old ITZ between the original natural aggregate and the adhered mortar, and the new ITZ between the adhered mortar and the fresh cement paste. The adhered mortar within this new ITZ layer contributes to increased porosity, allowing greater water absorption and altering the overall water to cement ratio. This results in a weaker microstructure with poorer bonding between particles, ultimately leading to reduced strength and durability in RCA concrete. One way to address the disadvantages of recycled concrete aggregates is through a method called carbonation treatment. This treatment involves curing the RCA with carbon dioxide. When CO2 interacts with the old mortar on the RCA surface, it creates a denser, stronger outer layer. This is shown in the illustration on the right side of the slide, where carbonation changes the surface chemistry by producing calcium carbonate. These chemical reactions help fill pores and strengthen the old interfacial transition zone, making the RCA particles denser and improving their mechanical properties. Natural aggregates and recycled concrete aggregates need to be washed and dried before adding them to the mix. For the recycled aggregates, once the materials have been dried, need to be placed into the carbonation chamber for 24 hours to start the carbonation treatment. The recycled concrete aggregates inside the chamber are exposed to CO2 gas at a concentration of 12%, temperature of about 23 degrees Celsius, and around 65% relative humidity levels. This carbonation process allows the CO2 gas to react with the old mortar on the surface of the RCA particles. As shown in the diagram at the top, these chemical reactions form a denser and stronger outer layer by producing calcium carbonate and silica. The photo on the bottom right shows our actual RCA samples undergoing this carbonation treatment in the lab. Carbon nanotubes, or CNTs, are tiny tube-shaped materials at the nanoscale made from rolling sheets of graphene. They have great potential to make concrete stronger and smarter, but there's a challenge. CNTs naturally clump together because of something called van der Waals forces. To fully use their potential, CNTs must be evenly dispersed throughout the concrete mix. We achieve this by adding CNT powder into water along with a special chemical called a surfactant, which helps separate the CNT particles. Then we applied a technique called ultrasonication, where high energy sound waves break apart the clumps, distributing CNTs uniformly in the water. The result is a stable CNT suspension that's ready to mix into concrete. Properly dispersed CNTs help make the concrete stronger, more durable, and even give it smart properties like self-sensing abilities. Results reported in the literature have consistently demonstrated that properly dispersed CNTs enhance concrete strength and durability, and can even provide smart properties such as self-sensing capabilities. In our study, we developed different concrete mixes to evaluate the effects of using recycled concrete aggregates, carbonation treatment, and carbon nanotubes on the properties of concrete. We prepared 4 different concrete mixes: our control, which is our standard concrete; our control CRCA mix, which is our carbonated RCA without CNTs; our CNT mix, which is our standard concrete with CNTs; and our CNT CRCA mix, which is our carbonated RCA with CNTs. Each mix used cement type 1L standard cement, natural aggregates or recycled concrete aggregates, both in saturated surface dry conditions, and carbon nanotube suspension when applicable. The exact proportions of water, cement, sand, and aggregate used was maintained at a ratio of 0.51, 1, 2.63, and 2.04 to ensure consistency and comparability. The concrete mixes were prepared according to ASTM C192 standards, and the fresh concrete's workability was measured using the slump test, ASTM C143. For evaluating strength, we cast concrete cylinders 4 inches by 8 inches, cured them at controlled conditions, and tested their compressive strength after 7 and 28 days, following ASTM C39. The graph presented here shows the water absorption characteristics of the aggregates. The carbonation treatment significantly reduced water absorption by approximately 35%, improving the quality and performance of recycled aggregates to be comparable with natural aggregates. To verify the carbonation treatment of RCA, we performed thermogravimetric analysis on the RCA and carbonated RCA mortar surface. TGA is a technique that measures how a material's weight changes as it is heated. This helps us identify different chemical compounds present in the materials. In the graph, the red line represents untreated RCA and the green line represents RCA treated with CO2. We observed 2 main regions of weight loss. The first region, marked in red around 400 to 500 degrees Celsius, indicates decomposition of calcium hydroxide. The slightly reduced weight loss in the carbonated sample suggests that some calcium hydroxide was consumed during carbonation. The second region, marked in blue around 600 to 800 degrees Celsius, indicates decomposition of calcium carbonate. The increased weight loss in the carbonated sample confirms the formation of CaCO3 due to CO2 curing. These TGA results clearly demonstrate that the carbonation process effectively converted calcium hydroxide into calcium carbonate. This chemical change densifies the surface of RCA as shown from the reduced water absorption in the previous slide. To understand how carbonation treatment and carbon nanotubes affect the fresh properties of concrete, we performed slump tests following ASTM C143. The natural aggregate concrete exhibited a slump of 9.75 inches, indicating good workability, typical of conventional concrete mixes. After carbonation, the slump decreased to 5.25 inches. This reduction in slump corresponds to the decreased water absorption. We previously observed through the TGA and water absorption tests that we have a denser aggregate surface after carbonation. With the introduction of CNTs, the slump increased to 11 inches, indicating improved workability and flowability. CNT dispersion likely contributed to lubricating effects, enhancing workability. Interestingly, the CRCA concrete containing CNTs exhibited a significant reduced slump at 1.75 inches, likely due to a combined effect of denser aggregate surface due to carbonation and the presence of CNTs. To assess how our concrete mixes performed in terms of strength, we conducted compressive strength tests on cylindrical samples following ASTM C39. We tested the samples at 7 days and 28 days. Natural aggregate concrete shown approximately 47 MPa at 7 days and 54 MPa at 28 days. Typically using recycled concrete aggregates in concrete mixes can reduce their strength due to presence of weaker old mortar layers. However, our results indicate that carbonation significantly enhances the properties of RCA. Carbonated recycled concrete aggregate concrete exhibits similar strength to the natural aggregate mix, reaching around 48 MPa at 7 days and 53 MPa at 28 days, indicating the carbonation effectively overcame the typical strength reduction associated with recycled aggregates. When we introduced carbon nanotubes into the mixes, the compressive strength improved notably. This enhancement is due to the CNTs reinforcing the microstructure, making the concrete denser and more cohesive. The CNT concrete mix achieved a higher strength compared to both control mixes and exhibits results similar to those reported in the literature. The combination of CRCA and CNTs exhibits the highest strength of all mixes tested, reaching around 51 MPa at 7 days and exceeding 59 MPa at 28 days. The results indicate that CNT reinforcement effectively compensates for any residual weakness in the recycled aggregates, resulting in a concrete that not only meets structural requirements but also offers enhanced environmental benefits. These findings demonstrate that using carbonation treatment recycled aggregates along with CNTs is a viable and sustainable solution for concrete construction, delivering both strength and ecological advantages. This research demonstrated that carbonating recycled concrete aggregates significantly reduces water absorption and improves mechanical performances. As confirmed by TJ analysis, carbonation allows CRCA to achieve strength similar to natural aggregates, making it a viable, sustainable alternative. The addition of carbon nanotubes further enhances concrete strength through improved microstructure. Our strongest mix combines CRCA and CNTs, indicating these two innovations have complementary effects. Future work will focus on assessing long-term durability, advancing our goal of resilient infrastructure solutions. Thank you all for listening to my presentation. Are there any questions?
Can I have the representative raise their hand one more time, please? It seems like there is not a representative from Wayne University, so we will move on to the next presentation. Can the representatives from Chittagong University please raise their hand? All right, we'll get this one started.
Hello, I'm Shafayat Rahman, an undergraduate researcher from the Department of Civil Engineering at CHUET. Today, I'm going to walk you through how AI-powered digital twins are revolutionizing structural safety. This is a major shift from traditional reactive maintenance to predictive intelligent monitoring using cutting-edge technologies like AI, drones, and real-time sensors. We are facing a massive global challenge. Over 7% of US bridges are structurally deficient, and the global infrastructure repair backlog exceeds $9.1 trillion. Traditional inspection methods are slow, they are costly, and they often miss hidden flaws. On top of that, manual inspections put human inspectors at risk. So these inefficiencies are no longer sustainable. We definitely need smarter, scalable solutions. Let's compare the old and the new. Traditional methods rely on visual inspections, manual data collection, and human judgment, all of which are slow, subjective, and hazardous. On the other hand, AI-powered inspections are automated, objective, and highly accurate, with up to 99.7% crack detection accuracy and a 75% reduction in inspection time. These systems deliver better results at a fraction of the cost. Well, at the core of this transformation is the digital twin. So that's a virtual replica of a physical structure. These twins integrate live data from sensors, 3D modeling, and historical tracking. They don't just capture the current state of a structure, they forecast deterioration, guide maintenance decisions, and provide complete digital traceability. In short, digital twins bring infrastructure to life in the cloud. The backbone of this intelligence is AI, especially convolutional neural networks trained on large datasets like SDNet 2018. These models detect cracks as small as 0.06 millimeters with 99.7% accuracy and 99% F1 score. They work with drone footage, classify different types of damage, and process thousands of images, all in minutes. The result? Fast, precise, and scalable assessments far beyond what human eyes can do. Here's a real example. The 140-year-old Stone Arch Bridge in Minneapolis underwent an AI-powered digital twin upgrade. Over 13,000 drone images were used to build a detailed model. The results? A 20% reduction in inspection time, up to 15% savings in rehab costs, and only 4 days of closure instead of weeks. This case shows how digital twins enhance precision while minimizing disruption. Well, the return on investment is remarkable. AI-powered systems cut inspection labor costs by up to 30%, reduce maintenance costs by 25%, and extend asset lifespan by as much as 40%. Operationally, equipment failures drop by 70%, and unplanned downtime is cut nearly in half. These aren't just statistics. They are industry-proven results from real-world implementations. Well, implementing a digital twin system follows 3 key phases. First, data is captured using drones, LiDAR, and sensors. Second, that data builds a high-fidelity 3D model integrated with existing asset systems. AI models are then trained for the specific structure. Finally, the system is deployed with real-time monitoring and predictive maintenance, and it keeps learning and optimizing as new data flows in. So looking forward, this technology is built for scale. Cloud platforms allow nationwide deployment, and standard protocols ensure compatibility across roads, bridges, and tunnels. It also supports climate resilience, monitoring stress from floods, heat, and seismic activity, and adapting maintenance strategies accordingly. In a rapidly changing world, this is how we make infrastructure smarter and future-proof. So in summary, AI-powered digital twins aren't just innovation, they are necessity. With proven accuracy, real-world success stories, and unmatched ROI, they represent a new era in structural safety. As engineers, planners, and innovators, we now have the tools to shift from reactive fixes to proactive prevention, making infrastructure safer, longer lasting, and climate ready. Thank you. I'd be happy to take your questions. Thank you so much.
With that, we're going to go to the last presentation from Chittagong.
Our thesis was supervised by Professor Dr. G.M. Sadikul Islam sir. Without any delay, I would like to show you today's presentation outline. We will discuss about background of the study, scope of the work, objectives, methodology, resultant discussion, conclusion, and finally, recommendation for the further study. As we already know, to modernize the world, we are producing 14 billion tons of concrete every year, which is contributing 8% of global carbon dioxide emissions from this sector alone. So it's high time we should rethink our approach to modernization. To tackle this environmental challenge regarding carbon dioxide emission, there is a sustainable material that can be incorporated into concrete called biochar. Now the question is, what is biochar? Incorporate this as cement. Here is
Looks like we might be running into some technical issues with the video.
The objective of our study was to characterize
There we go.
biochar and evaluate its effect on cement and sand replacement. Then finally conduct life cycle assessment to investigate the environmental impact. These are the materials that we used in our study. Two types of biochar were used, BC400 and BC600. BC600 was made at 600 degrees Celsius using a lab furnace, which makes it more controlled but costly. On the other hand, BC400 was produced at 400 degrees Celsius in a simple peat kiln, making it much cheaper and easier for field use. This is the general outline of our methodology. After collecting the biochar, we test the characterization of this material. After that, cement has been replaced with biochar by 1 to 5% by volume with a curing age of 3, 7 and 28 days. Then sand has been replaced with biochar of 5 to 25% by volume with a curing age of 14 and 28 days. Then the necessary tests were conducted. Then we did a full-fledged life cycle assessment of our approach. In the experimental program, we characterized biochar through SEM, EDX, XRD, XRF, PST, and Lawson ignition test. Tests on a mortar sample were conducted to evaluate the fresh and hardened properties of the mortar. These are the mix design tables. Table 1 represents mix proportion for cement replacement and table 2 represents mix proportion for sand replacement.
Thank you, Shatabdi. Now let's focus into the results portion. Firstly, the characterization of biochar, and starting with ACM test result. So here the first row of image is representing BC600 and second row is for BC400. In the BC600, the overall structure has uniform porosity. These pores are like rounded honeycomb and outer surface is smooth. On the other hand, for BC400, the overall structure has low feedstock uniformity. Pores are mostly flaky, thin plate-like shape, and outer surface is rough. In the EDX test results, we found that BC600 has a carbon quantity of more than 90%. On the other hand, BC400 has more than 80% of carbon quantity. This percentage of carbon ensuring higher carbon sequestration capability of biochar. In the XRF test results, we found 25% of silicon dioxide and 35% of calcium oxide. This value helped in the strength gain of mortar, which we will see in the upcoming slide.
Now the test result from mortar samples. Firstly, cement replacement. Initially, we used a fixed water-cement ratio of 0.5 in the mix, but we observed very low flowability and poor strength performance. To ensure proper compaction, we adjusted the water content to achieve a flow of 139 plus minus 5 mm. As a result, the water-cement ratio varied between 0.7 to 0.77 for both types of biochar. This adjustment helped reduce voids and produce a denser mortar due to better compaction. From the flexural strength performance, BC 600 showed that the flexural strength slightly decreased up to 3%, but at 4% it showed higher strength than the control. On the other hand, BC 400 showed an increase in flexural strength up to 2% replacement, after which the strength gradually decreased. However, both types of biochar demonstrated satisfactory flexural strength performance, aligning well with the findings reported from the literature. From the compressive strength results, BC 600 showed an increase in strength up to 4% replacement with the optimum value of 31 MPa at 3%, which is about 8% higher than the control. In contrast, BC 400 exhibited strength improvement at every replacement level, reaching a peak of 33.9 MPa at 4%, which is 17% higher than the control. These findings highlight that incorporation of biochar at lower percentage can effectively enhance the compressive strength. The UPV results showed that all specimens had values within the standard range for good quality mortar, which is between 3.5 and 4 km per second. This indicates that proper compaction was achieved across all mixes. Now let's see the SEM of the paste sample. In the strength parameter, BC 400 was better than the BC 600 because BC 400 has a more irregular and rough surface and it is capable of making a bond with cement easily compared to BC 600, as you can see in the second and third columns.
Now let's see the test results on mortar sample for sand replacement. In the sand replacement, to maintain uniform compaction, the flow was kept at 35 ± 5 mm and water demand was adjusted accordingly. In the case of sand replacement, both flexural and compressive strength decreased with the higher percentage of biochar. This reduction is mainly due to the high porosity and water absorption of biochar, which affected the mix density and bonding. Now let's see one of the most important portion of our research, that is life cycle assessment. To conduct life cycle assessment, we used OpenLCA software. The dataset we used was EcoInvent 3.11. This is the latest dataset from EcoInvent. The boundary condition was set as cradle to gate. The global warming potential time frame was for 100 years and the impact assessment method was IPCC 2021. Firstly, let's see the emissions regarding biochar production. This is the model diagram of biochar production. The input flow was sawdust, electricity required to produce biochar, and the transportation distance. The output flow was 1 ton of biochar. Let's focus on the results. To produce 1 ton of biochar, 444 kg carbon dioxide equivalent will be generated. It seems pretty high value, though it is actually not, because as the biochar can sequester carbon, so the net climate benefit is more than 2400 kg carbon dioxide from the production of only 1 ton of biochar. So producing biochar is good for the environment until we allow it to decompose. Now let's see what happens when we incorporate this material into cement mortar. This is the model diagram of mortar production. This is the results from OpenLCA software. Let's focus into the graph only. In the control, the emission is 574 kg carbon dioxide equivalent. When we incorporate biochar at various levels, the emissions decrease gradually. At only 5%, the global warming potential reduction is more than 12%. It is a huge improvement for our climate condition. On the other hand, for sand replacement, the reduction of global warming potential is far more than cement due to the higher quantity of biochar. As you can see, at 25% replacement, we achieved a carbon negative cement mortar, supporting our core objective.
So, to conclude, this study highlights that BC 400 outperformed BC 600 in both strength and sustainability. At just 4% cement replacement, a 17% increase in compressive strength was achieved, along with the 10% carbon dioxide emission reduction, which is a significant result. Even with sand replacement, at 25% replacement, we were able to achieve a carbon negative mortar with minus 5.48 kg carbon dioxide equivalent reduction, which is remarkable considering the minor compromise in strength. Unlike conventional supplementary cementitious materials like fly ash, GGBS, silica fume, which mainly helps with strength, biochar not only enhances strength but also reduces a significant amount of carbon emissions, offering a dual advantage. Thank you.